matrix multiplication, assuming we have two matrices, and the two matrices, they are called A and B respectively. So we first, what do we mean by multiplying two matrices? This can be viewed as a mapping. Imagine a matrix can define a mapping, right, or a transformation. Suppose I have a B. Then if you give me an X, the vector, suppose B and X, they are dimensions match, then through B, I can get an image. We call it the image of X will be after multiplying the vector X by B. So that is the image. But if you apply A on the image of X, that means you can apply another transformation which is defined by matrix A. So let's say, suppose this is becoming the input for another matrix. So this image of X becomes the input for A. So this A is the matrix that defines a mapping or a transformation. So after this, what is the image of the BX? It will be A, because BX as the input, right? So we can have this. So that AB actually is defined to be such a matrix that maps X vector directly to this vector. So I want to show AB as a matrix. AB is another matrix. Certainly, it depends on the A and B, right? Separate two matrices. And the effect of AB is that you apply B first, right? So the AB is a mapping that maps from a vector X to the vector A on BX. So that means this mapping that AB defines is equivalent to two maps. First, by applying B to get B of X, then you get apply A onto this image of X. Apply A, you get A on the image of BX, X, right? So that's after you get BX, you apply A, you will get A on the BX. Yeah. So, and AB will be equivalent to that. So because of that concept, then we can try to look at such a matrix. So what is the matrix that defines this composite map? Composite map. That means B is applied first and then followed by A. So this, for whatever input, right? If you apply this map onto any X, that means you have to apply B first on X, and then later you apply A on BX. So that is the meaning of this map. It's a composite mapping. So our goal right now is to find the matrix. How do we calculate this matrix that represent this mapping, this composite mapping? So to get the transformation matrix of this composite mapping, we just think of the definition of this matrix, that matrix AB, right, should define such a mapping. Yeah. So if I have a vector X, and first of all, we apply B to get apply B on this vector X to get image of X. So what do we get? So the B, you see that's the B. And you see the first column, second column, the last column. Suppose B has n columns, because as we know, the B must have number of the number of columns of B should match the number of entries in this X, right? If X has n entries, the B must have n columns. So that's why we use both face letter B for each column. So that's the first column, second column, the nth column, which matches the n. So we can write this B times X will be linear combination of these columns. So yeah, that's the inner function, right? That's the inner function, B times X, which is just another vector. You see, a matrix times a vector. This matrix times the vector is just another vector. It's a linear combination of the columns of B. Now with this vector as a new input for A, so this is already this vector, right? This vector now, next one, what do? We will, after we get this Bx, we will apply A, that outer function. Let's apply A onto Bx. So next one is once we get this Bx, we apply A on Bx, which is A on this vector. That's the linear combination of columns of B. And then we can see that just A, by the property A, this linear mapping, right? So it's a linear, using the linear property, you just do each term, right? So we can apply A onto each term and then move the scalar multiple outside of A, because that's A is a linear mapping. As a transformation matrix, A defines a linear transformation, as we know. Any matrix defines a linear transformation. So here is, we're using the linear transformation property to get this. Now, do we realize that this part can be written as a column, x1, x2, xn, and this is a new matrix. This matrix has n columns. The first column is AB1. That means A on this. The second column is AB2. The last column, the nth column, is ABN. So what we have is that we have rewritten the ABX in such a form. So you see this ABX, which is AB, this mapping on NN vector X, right? Means you first apply B on X and then apply A onto the BX. So then as a result, we can see that it's a linear combination of these columns. So we can write these columns, total of n columns. And those are the weights, right? Each entry of X is a weight. So it's a different way of writing this. Then we realize A, B are defined. This is a transformation matrix. So for this composite transformation, which is called AB, its transformation matrix is totally defined by this. So the first column is just AB1, second column is AB2, third column or nth column will be ABN. So that is AB. That is the matrix that defines the transformation. Why do we say it defines the transformation? Because whenever you give me an X, I can find image of X using this matrix. So this is the matrix. For whatever X, you use this matrix to calculate image of X. So realize we have already defined a matrix corresponding to this transformation, composite transformation. Okay, now we're ready to use this method. So this method is that whatever X you give me, I can calculate the image of X under this composite transformation. And by multiplying X by this matrix, that is the transformation matrix corresponding to this composite transformation. So we have defined AB, A times B. A times B corresponding to this matrix. That means A times each column of the second matrix B. So, okay, A times B is equal to just A times first column, the second column, the last column. So you have total of n columns, right? That's the product. So with that, then we know how to multiply A by a column. Let's just go ahead, look at one problem. So we have arrived at this formula, use that reasoning, and then we can in the transformation point of view, right? This is the transformation matrix for that composite transformation. Then this matrix is simply this, assuming the matrix B, its n columns are B1, B2, Bn, etc. So the product is simply AB1, AB2, ABN. So we can find n columns of the product matrix. Then we found the matrix, because if we have found each column of the product matrix, then we have found the matrix. So see this example. This example A, B, decide the product. Now, is it legal to multiply? Let's see. A times B. A is what? 3 row, 2 columns. The B is 2 row, 4 columns. And are we able to multiply A by B? Let's see. Can we multiply A by each column of B? So yes, we can look at each column 2 entries, right? Yeah, we got 4 columns, you see, B1, B2, B3, B4, 4 columns. And then all we need is to multiply A by each column. So let's calculate this A times B1, the first column, which is this. Can we multiply? Is it legal to multiply A by that first column? we must check the dimension, right? Let's see how many columns in A. 2. How many entries in this first column of B? 2. So that's totally fine, right? So you see 2 entries here and 2 columns in A. So this linear combination of the columns of A. So we can immediately multiply because we know it's 2 times first column, right? Plus 0 times the second column. It's a linear combination of the columns of A. And then as a result, we get 2, 0, and 2. We get a vector. So that is A times the first column. And similarly, we can multiply A by second column of B. And then A times third column of B and A times fourth column of B. So we can multiply with each time we multiply, we get a vector. That's the okay. So after we get A, B, 4, then we are ready to write the product matrix. So AB1, AB2, AB3, AB4, then what's the product? So A times B is just A times each column of the matrix B. And then we find AB1, AB2, AB3, AB4. So we put all these, you see the AB4, right? That's here. That's the A times B4. So as long as you use proper notation, that can make your work very simple and clear. This B, we denote that matrix B by 4 columns. You see? There are 4 columns. And A times each column of B to get corresponding columns of the product matrix. Okay, that's an example. So you can do matrix product. So when you do this, be careful this A. So in this case, A is 3 by 2. The B is 2 by 4. And you see these two numbers must be the same. The A times B, the second matrix, its row number must be equal to the first matrix, its column number. As a result, we get 3 by 4. The resulting matrix, AB, is a 3 by 4 matrix. So as you noticed, 3 by 4. So 3 row, 4 column. Yeah. So if A times B, can we multiply B by A? Is that possible? I want to ask you if you think it is possible or not possible. So B, 2 by 4. If I want to try to do the B times A is 3 row, 2 columns. These two numbers are not the same. So if I multiply B by A, then let's see, each B is a 2 by 4 matrix, 2 by 4. But if I take a first column of A, it will have 3 entries, right? So suppose 3 entries. Let's call it A1. With 3 entries. Yeah, does not match the number of columns of B. So you cannot swap. So AB is not the same as BA in general. So just be aware, we do not have commutative property for the product. Yeah, matrix. The order is important. Sometimes you can multiply A by B. For example, this case, you cannot multiply BA. It's not even possible. So sometimes it's possible, but still AB is not necessarily the same as BA. So anyway, in general, we should not just think AB and BA. They're really in generally they're not the same. So now with this approach, there's another approach. For example, we know that ABJ will produce the jth column of the product matrix. By AB, if I want to take only the jth column, this product matrix, then its jth column will be A times the B matrix if I take only the jth column of the B. So this, we know that will be the A times the jth column of B. Then this will be the jth column of AB matrix. Yeah, so AB, the matrix, it has the jth column. So that's this one will be this. So it's a jth column, but what if I want to find the ith entry of the jth column? Then we just need to multiply a little more. That is, as you can see, a linear combination, right? This B1J times first column, and then B2J times the second column, because we just expand. It's a linear combination of the columns. So we just rewrite the same thing. Quantity, it's a different way of writing this. Just write as a linear combination of the columns. What do we do next? We can just write after this. This is just a vector, because a linear combination of these many vectors is just a vector. So we can add all these vectors together. Then you see a vector. So this vector, I want to focus on the ith entry. You see the first entry, this. Second entry, the ith entry, right? This is the last entry. Yeah, the ith entry follows the similar pattern. It's just this vector, this, you see the first entry is 1, 1, 1, 2, 2, J. So then the ith entry for the jth column will be this. So this is a process to get the ith entry, and that means this is the jth column of AB matrix, but it's ith entry. So you see the AB matrix is a matrix, right? Now you single out the jth column. So this matrix, now you only focus on the jth column. With the jth column, which is this vector. But I want to pick the ith entry of the jth column. So then you get a particular entry, which is Aij of the product matrix AB. So here is the formula. This is the formula. That is a formula to calculate a particular entry of the product matrix, which is Aij. So this formula is very convenient. Okay, so just to get any entry you want, for a product of two matrices. So let's look at an example. So here is an example. A, B are given. So as you can see, A is the same A, 3 by 2. B is 2 by 4. And I know the product matrix will be, because these two numbers are equal, so 3 by 4 will be a resulting matrix. So 3 by 4, which is the product matrix. Instead of calling AB, I call it C, which is the same, just a different letter to represent the product. So for the simplicity, right? C is the product of AB. So how do I denote each entry of C? Because it's 3 by 4, I have 3 rows, and each row has 4 entries, so 4 columns. Okay, so 3 by 4, that's the matrix I write as C 1 1 1 2 1 3 1 4, 2 1 2 2 2 3 2 4, C 3 1 3 2 3 3 3 4. So now can we find any entry? Yes. Suppose I want to find C 2 3. Let's do. This time the approach is different. In that we can just find each entry of the product. So using, for example, let's do C1 3. C1 3, that means we're going to use first row, third column. First row of A, third column of B, 1 and 3. So this first one, we have to use the first row entries of A. The second number 3, we will need the third column of B. So then what do? We will multiply their corresponding entries. So you see 1 times 1 times this one, 0. That's a 0. 1 times 0 plus 2 times 5. Yeah, so we get a 10. So therefore, this is 10. So we just got this entry as 10. You can find any entry by this formula. Suppose you want to find, how about 2 4? This 2 4 entry of the product. This C, the product matrix. That means we need to use second row of A, fourth column of B. Second row, 2 4. Second row of A, fourth column of B. So let's multiply. So 0 times 1, this first entry of this vector times first entry of the other column vector. So 0 times 1 is 0. 1 times 0 is also 0. So you get 0. So this will be 0. So then we can get, right, using this approach, we can find every entry. So finally we get a product matrix. Do you notice the difference? In this approach, we find the product of two matrices. Each entry is calculated using that formula for each entry. So each entry is calculated. So if you want to calculate ij's entry of the product, what do? You just use ith row of A, j's column of B. And find a number. That's the inner product of the two vectors. So I just show, for example, if I do this, first row of A, first column of B, then you will get one entry of the product, because the first row of A, first column of B. How do you calculate the 1, 1 entry? That means we do, okay, 1 times 2 plus this is 2 times 0, 2 times 0. So what is the result? So 1 times 2 is 2. 2 times 0 is 0. So it's 2. So that's why we get a 2. So that's the 1, 1 entry. That's the entry at the first row, first column. Okay, so now this is the one approach. It's very easy to use. Just find every entry in this way. So another approach, as I mentioned earlier, then you just, instead of doing this, you quick look one more time. So instead of entry-wise, to find the product of AB, you can multiply A by each column of B. So you will get the first column of the product, second column of the product, right? And then the third column of the product by multiplying the first matrix by the corresponding column of the B. Yeah. So if A times B1, that's the first column to be found. A times B2, that will be second column. Times B3 will be the third column. So of B. So that's another alternative approach to find the product. So product is taking more work, but it is yes, once we define it clearly, you know how to do it. And then one more quick property review. The product of 3 matrices, as long as the dimensions match, and we have the associative property. You can do AB first or BC first. Associative property. You have distributive property. A times the sum will be equal to AB plus AC. That's the distributive property. And you have the sum times C equals A times C plus B times C, AC, BC. And you have scalar multiple times a product. You can put a scalar multiple anywhere because that doesn't affect your result. C can be with A, or the scalar multiple can be with B. So you can do it anytime. It doesn't change your result. Or you can do it at the very end after you multiply AB and then do the scalar multiple. So scalar multiple can be placed anywhere. If you have a scalar multiple times A times B, then you can use any of these orders to do the scalar multiple. And identity matrix times A is equal to A times identity. Yeah, identity is kind of like a 1 in numbers. So it times A doesn't change A. But be aware this A, if it's M by N matrix, you multiply this identity from the right-hand side, then the identity must be M by N matrix. If you multiply A from the left-hand side, then the identity must be M by M identity matrix. So that square identity matrix, the dimension has to make sure that it's possible, right, to multiply, because these two numbers must match. Okay, so once we know the product, we know the numbers. Two numbers, if the product of two numbers is 0, we know one of them must be 0. But it's not true for matrices. if two matrices, the product is 0, it's not necessarily true that one of the two has to be zero, right? So, for example, this A and B, the product is 0. However, it's possible that this matrix A and B, neither one is 0. Yeah, for matrix, it's possible that two non-zero matrices can produce a product of 0 matrix. So this is different than the property of numbers. So when you see a product of two matrices is 0, it does not mean one of the two matrices is 0. So be very careful. That also means if you have AB equals AC, can we say we cancel the A, then B is equal to C? Can we come to that conclusion? Also, we need to be very careful. Can we cancel A? Well, let's do it very carefully because AB equals AC. If they are equal, that means the difference is 0. That's equivalent to, by the distributive property, A times this is 0, right? If we can apply that property. A times B minus C is 0. Now, we know that when the product of two matrices is a 0, it doesn't imply B minus C is 0. Excuse me. So that means when the product is 0, then it's not necessarily true that A is 0 or that is 0. We just talked about that case, right? So if B minus C is not necessarily 0, then B is not necessarily equal to C. So we cannot say AB equals AC, then B has to be equal to C. That's not necessarily true.